All right, here we go. So, lights are on. Who wants to take a walk?
I do.
Yeah, I think Kristen was first. Just walk back towards that door and the lights will come on. The sensor's back there. All right. What's the last thing we were talking about? Hydrogen and helium?
Yeah. Hydrogen, helium, yeah.
All right, what did we learn?
Helium is not
You gotta act like you're going in the door. The back door. Trust me, act like you're going in. Booyah. Come back, please. Thank you. Because they're on a sensor, a motion sensor, which is in the back of the room, which makes all the sense. Sorry. All right. What do we learn? Hydrogen is most abundant in the universe. Why? What's made of it?
Stars.
Stars. Good. What else did we learn about it?
Flammable.
Flammable. Is helium flammable?
No.
No, that's because it's
Inert.
inert. It's stable. It's stable. Now, our sun will take two hydrogen atoms, fuse it together to make helium. It's called nuclear fusion. That produces a ridiculous amount of heat. You can feel it, and it's 95 million miles away. So, when the sun runs out of hydrogen gas and it's all helium, what happens?
It dies.
Yes, it stops working the way it's supposed to. It basically dies. Here's the issue, and I think I told you this before. Inside the sun, that's where the photons come from. So when a photon of light, what's photons? These little particles of light. They're hitting you right now from the lights, from the sun. When a photon of light is produced in the core of the sun, it bounces around for 100,000 years before it gets to the edge of the sun, and it takes 8 minutes to get to us. 100,000 years to get from the center of the sun to the edge, outer edge of the sun, so it can go into space towards us. Okay? That's crazy. Think about it. 100,000 years. So the sun could maybe now not be producing photons. We wouldn't know. Let's say it started today, not producing photons in the core. We wouldn't know for 100,000 years.
Maybe dead.
That's probably not accurate. I'm being dramatic. There are people that get paid probably tons of money to just watch the sun all day, every day, make sure there's no weird things happening, because the sun can send out, what can it send out that can hurt us?
Ultraviolet rays.
Ultraviolet rays, what else? Lots of other things too that our magnetosphere protects us from.
Probably stupid, the solar visions or whatever.
Oh, all right, no, you're right. Solar what? Starts with F.
Fusion. Flare.
Flare, solar flare. There are these coronal eruptions. There's these things that can be flung off the sun towards us. Lots of charged particles. Well, if our Earth gets hit with enough of those, it can basically wipe out our electrical infrastructure and basically knock out all the power. And
That's a bad day.
yeah, it can happen. At some point in the 90s, it hit us, and between the U.S. and Canada, there was like millions of dollars of damage. But we wouldn't know. We're here doing normal things, but there are people paid to watch the sun. Anyways, moving on. What else? That was it for hydrogen and helium. Real quick about group 17. They are unique compared to all other groups because they have all three phases. So if you look over there, which two are gases? Fluorine and chlorine. Who's the liquid? Bromine, and then iodine and acetylene are solid. So it has all three phases. I just wanted to bring your attention to that. We don't necessarily have to break that down. Oh, and iodine can do what?
It could go from a solid to a
Sublime,
gas.
right. Sublime. I am going to show you that. I just haven't got around to that yet. All right. Good. Write this down. 7 diatomic elements. 7 diatomic elements. What the heck does diatomic mean? I will show you with magnets. Do you guys know that not all metals are naturally magnetic? Now you know. Name one metal that is naturally magnetic. So if you have this metal in a rock, let's say, that you find when you're digging for research purposes, the magnet will be attracted to it. One metal that everybody knows is magnetic. Iron, right. Good. Now, this here, all these red little circles are atoms. They're very closely packed together. Okay. You don't have to draw this, just pay attention here. Over here, we'll do this. Okay. These green ones are also atoms, but when they're touching or perhaps overlapping, is a better way to show you. What are they called? Two atoms chemically combined. What's that called? Bonded, good, very good. But there's a name for this. That's an atom. That one green one is an atom, but together they're not atoms. Molecules. So this is what I mean by that word right there, diatomic. Di means two. Two atoms together is diatomic. We call that a molecule. So you do need to write this down. So just draw one circle, call it an atom, put two together, call it a molecule. So 7 elements on the periodic table do not exist like this. These are a bunch of atoms, very close together. Now, does this look like a solid, liquid, or gas? Solid. What's this look like? Liquid or gas? I'm trying to go for a gas there. Maybe I spread out a little more. So this would be a solid monatomic element like calcium, for example. You don't have to write this, just watch this. Okay, calcium would be very close together, tightly packed, because they're solids. It's a solid, neat, ordered rows. But gases would be kind of all over the place, spread out. And if it's diatomic, that means the symbol would be something like this. Oxygen would be O2. So you have two O's. One O here, one O here. That's how oxygen exists. It's one of the 7. So I'll list them all in a second. Just trying to get you to visualize the difference between diatomic, which are molecules, and then just monatomic, which means just one atom. So there's 7 of these. You need to memorize them. Now, before I move on, which one is more dense? Raise your hands, please. The calcium or the O2? Which the way I drew it here with the magnets, not drew it, when I put the magnets up, which one is more dense, or which one's less dense, whatever. Excuse me, sorry, you want to explain? Well, is which, more or less? More dense, how do you know? Good. Density, very good. Density is all about how closely packed the atoms are. I may have said this earlier this year. This is very dense because they're really close together. This table, really dense. Particles are really close together. The air is like this, a gas. Particles are more spread out, less dense. Okay, it's all about how close those particles are together. Okay, that's important to understand density. Not, well, notice I didn't say this. What does density have nothing to do with, really? The mass or weight of it has nothing to do with it. Okay, because if I was holding a pound of air, just imagine I could do that. And I was holding a pound of copper. Okay, which one would take up more space in my hand?
Wait, a pound of what?
I have a pound of copper and a pound of air.
Yeah.
Which one would take up more space? The air. Yeah, the air, because it's spread out. So if we were to use the same number of particles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 4, 6, 8, 10. I could add 2 more. This is exactly what it would look like in real life. This is just like zooming in. So that's taking up more space on the board than this, because this is tightly packed. So the more dense it is, the less space it takes up. It has nothing really to do with mass. Okay? It's about how far apart the particles are. It's really important to understand that. All right, so these diatomic elements are all gases except one liquid. And here's the phrase. Hunkelbrief.
That's great.
That's the acronym. Hunkelbrief. So what 7 elements? You with me?
Helium.
Bottom, back there? Okay. What's the first one? Hunkelbrief. H, hydrogen, good. Write it down. H, next. Oxygen. Nitrogen. Hunkelbrief.
Okay.
Close. Chlorine. Close. Cl. Can't remember lowercase l there. Hunkel and then brief. Bromine. Iodine. Fluorine. There's the 7. And they all get a little 2 on the bottom. H2, O2, N2, Cl2, Br2, I2, and F2. Those 7 elements only exist in pairs when they are by themselves. What the heck does that mean? Well, water is H2O. Well, wait a second, you just told me water, oxygen is diatomic. How come there's no 2 there? Because when it forms a bond and it's in a compound, it changes. But if oxygen is just free in the environment, in the air, it's O2. So when oxygen's by itself, it gets that little 2. If it's in a compound, it may or may not have that 2. So this is when the element it's in its pure state is what we said. By itself in its pure state. So H2, O2, N2, Cl2, Br2, I2, and F2. Hunkelbrief. Just a weird little thing. I did not make that up. That's a thing that other teachers use. So Hunkelbrief, if you say it enough, you'll remember. And those are the 7. You do need to know that. Okay, you need to remember that. It makes your life easier. All right. Okay, last thing. I want you to, on the paper, on your notes, I'm going to walk around and check. Write down the nuclear symbol for, let's pick one on the quiz tomorrow.
Oh, yeah.
Nuclear symbol for cobalt. And if you don't know what that means, just write down what you can. We'll go over it. Nuclear symbol for cobalt.
Where do you want it?
Right in your notes. I'm going to come around and check. So, nuclear symbol. Are we good with this marker still? Willow, can you read that still?
Not really.
Not really. Okay. We'll get another one. Nuclear symbol. What is the nuclear symbol for cobalt? You definitely need your periodic table for this. And there's 2 words, nuclear and symbol. Nuclear means nucleus, symbol means symbol. Let's see. See who's a hero, who's a
Say it.
0.
And then,
Oh, you asking if that's correct?
yeah.
1/3 of the way there.
Oh, bro, I got
Nuclear.
one.
I got the symbol part, now we can nuclear part.
All right, you're 2/3 of the way there.
I have no idea.
You have a lot to do there. But your method is correct.
All right. Hey, you know.
Close, real close.
I don't actually know.
You're get rid of that part of it, and then you're 1/3 of the way there.
I have no idea. I don't know what that
You don't need this,
is. The
and
bottom number?
and then you're close. You're getting there. Still waiting.
I don't need the bottom number? Like the electron?
You don't need the electron configuration. All right, congratulations. Everybody, almost everybody had CO. Now, I'm going to highlight Kieran for a second. So, what's the difference between this and that?
Oh, wow.
Oh.
Good. So, and it's just maybe how you drew it, I don't know. But, and I'm not making fun of you. I'm just using it as an example. This is a common mistake.
That's the handwriting.
Carbon, oxygen, this is cobalt. So if you put a capital O, then, that's oxygen. Lowercase, then it's just part of the symbol. So just be careful with that, okay? So that's all. Just be careful.
Put an arrow that says little.
All right, that helps. All right, so that's 1/3 of the nuclear symbol. That's the symbol part. Nuclear stands for nucleus. What's inside the nucleus? Protons and neutrons, which together make up the mass of the element. So, you need a number here and a number here. And the good news is the periodic table sets it up for you. We did one of these maybe yesterday or the other day. The mass number goes in the top left and the atomic number in the bottom left. So what's the atomic number of cobalt? 27 goes in the bottom left here. And the top left is not the atomic mass, because that's with all the decimal points. We want the rounded version of that number. That's called the mass number. I know that sounds crazy. It's 2 different things. Atomic mass has the decimals. Mass number is rounded. So, Caroline, what is it? 59. That is the nuclear symbol for cobalt. That is the nuclear symbol for cobalt. So again, why is it called nuclear symbol? Because this number says, all right, I have 27 protons. They're in the nucleus. And by the way, they're positive. How many electrons does this have?
27.
If it's neutral,
27.
27. And they're negative. They add up to 0. Who knows how to find the neutrons? We don't really need to know this yet in this part of the year, but we'll go over it
I
real
don't even
fast.
know where I got my numbers from.
I'm going to give you another hint.
Pretty long.
If the neutrons plus the protons equal the mass, you can figure out how many neutrons based on what's on the book. So neutrons plus protons equal the mass. What's the mass of this symbol here?
59.
59. Let's label that. Go ahead and label that. That's the mass number. Go ahead and label that. And the bottom one is your atomic number. So if neutrons plus protons equals mass, you can figure out the neutrons by doing what?
Subtracting 59, 27 from 59.
Right, 59 minus 27. The answer is
30 something.
32 neutrons by subtracting them. That works every single time. So anyways, we don't need to know that yet, but now you do. So what is a nuclear symbol? Mass number on top, atomic number on the bottom. Your periodic table sets it up for you. Over there is all screwed up. Don't use that, okay? Mass on top, atomic number bottom. So we're going to use a nuclear symbol a lot, so you have at least one example. We'll definitely come back to that. All right. Okay, so I think that was it as far as using a periodic table. Don't forget the quiz tomorrow on all the circle elements. You'll do that as soon as you get in here. I'll probably have you hand in the homework because I'm not here. If he wants to go over it, then I'll let him go over it, and then I don't know. I'll talk to him. Maybe he'll just check it, and then you can keep it. But I'll probably have him go over it too. All right. So let's talk about what's new here. We got some time. 12 minutes ish, a little more, 13. Okay. We got a beaker. We got an Erlenmeyer flask.
No.
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 Erlenmeyer flask.
No.
Graduation.
You're wrong. Incorrect.
No.
That's not
Someone's looking at me like, what is he doing?
Yeah.
I'm just screwing around. What is this called? Graduated cylinder and a beaker. Okay. Notice the markings on the two of them. All right?
Very nice.
Hey, do you have those glasses off, Olivia? No? Must be someone who looks just like you wearing the same clothes, not wearing glasses. Did you have the glasses on all day?
That's creepy.
What's creepy?
You like memorize
No,
what
I
people
walked
wear.
by someone this morning, looked just like her with the same outfit, no glasses. I was like, huh, she must wear contacts.
That's true.
Okay. So, which one do we use for measuring volume? Why? More accurate, okay. Give me another word.
Precise.
More precise, perhaps, okay. Did anyone pay attention to the numbers on here?
Not exactly.
From what to what?
0
0 to 100. What about here? 0 to 200, right. Okay. So, if we have a graduated cylinder with a whole bunch of marks, let's say between 0 and 50, and then we have a beaker with maybe like 3 marks between 0 and 50, and I say, oh, I don't know, Jake, I need 25.2 milliliters. Would it be very hard to use this?
Yeah.
Yes, because let's say if there's only 3 marks, I mean, that we'll say 4 to make it easier, okay? The 0. All right, we'll make 5 marks to make it easier. 10, 20, 30, 40, and then 50, right? So each line is 10 milliliters. So if you wanted, what did I say? 25.2? 25.2 between 20 and 30. So you have two lines here. Here's 20, here's 30. 25.2, I don't know. Here-ish? I don't know. So you have to guess. That's a crappy measurement. But here, maybe they go up by 0.1, 0.2, 0.3. Okay, maybe there's enough lines where it probably wouldn't go up that small of an increment, but it'll go up in a smaller increment. So if we use this one, we can really only measure volume in tens. So like 10, 20, 30. So, you know, we could get something like 20. That's the closest we could get to 25 and be accurate. Here, maybe we could get 25.2 exactly. Well, how many numbers are here? 1, 2, 3. How many numbers are here? 2, sort of. If I wanted to measure the length of this room, what would I use? Would I use this marker?
Well, yeah.
Could I use the marker?
Yeah.
Could I like put it against the wall, then flip it and flip it, and then, you know, it takes 622 markers to get to that end, all right?
Feels like you've done that.
And then you would measure this with like a ruler and then multiply it by the number. That sounds ridiculous. Autumn, you with me? You need to stand up and like move around and wake up, do that. What about a meter stick?
That'd be a good option.
Yeah.
Not bad, right?
How about yours?
Is it better than using a marker?
Yeah.
Yes. What about a ruler?
No.
Probably better to use this, maybe?
Yeah.
What's even better that I don't have here?
Tape measure from the
Yeah, tape measure. Okay, so we got a 100-foot tape measure. That would work. That would work better. And those, some tape measures really have a lot of graduation marks. That's what these are called. Graduation marks. Why it's called a graduated cylinder. What am I getting at? The next thing we're going to learn about is, write this down. So I'm trying to make it more relevant because it is kind of an obscure topic. Significant figures. So what I was getting at with the beaker and the graduated cylinder and the measuring tape versus a marker, some measurements are more significant than others. This graduated cylinder will give you a more significant measurement than this beaker because there's not as many graduation marks. Okay? Imagine we had a scale, and the scale measured in increments of 10 pounds. Okay, you get on a scale and it says 130, but really you're 137. Well, those 7 pounds don't register because it only measures in 10 pounds. That's ridiculous. That no one would make a scale that way. But that's not very significant. Or you could have scales that go out to the hundredths place. How many decimal places is that? 2. 2. Versus a scale that just rounds to the whole number. The hundredths place is more accurate, more significant. So the more decimal places, so again, 25.2 versus 20, more significant. Where is this used? Why are we talking about it? This is where we're talking about it. This is why we're learning. Some pieces of equipment in chemistry, science, and life in general are more accurate, more significant. Okay? So the rules to figuring this out is what we're going to learn today, and that's what your homework's on. All right? So, does it make sense that number is more accurate, more significant than that? Because of the decimal place? Yes, we agree?
Yeah.
Yes. Amber, you with me? You too. You need to walk around, wake up, and do that. All right. Now, a little geography lesson.
No.
So, if you can draw the U.S. of A, go ahead and draw it.
Oh my
I can't.
God.
But I'm
Are you
going to
serious?
I'm just going to do this. Here's USA.
Oh.
Here's California. Here's New York. Okay. All right.
Yeah.
So here's our country. You can do the same. You need to do that or draw it, something to that effect. You need to write our country right in the middle of the paper. So a little geography lesson. I'm going to California. I want to go swimming off the coast into the ocean. If I keep swimming, I could hit Hawaii, then Asia. If I'm in New York or Maine, let's say, and we go swimming, what are you going to hit eventually? Yeah, Europe. Okay, good. All right, here's the question. Hopefully you guys can get it right. What ocean's over here? What ocean's over here?
Atlantic.
The Atlantic's over here?
No.
The Pacific's over here?
No.
This is the Pacific?
Yeah.
Are you sure?
Yeah.
I hope so. Pretty sure.
Okay. Go ahead and write that down. Good job. You guys passed the geography test. Now you can learn the chemistry part of it.
Can't wait.
Okay, Pacific really means, and this is the part you're going to learn about sig figs. We abbreviate sig figs. What it really means is decimal point present. Atlantic means decimal point absent. So why the heck am I using Pacific and Atlantic? Because A means absent, P means present. And actually, I got to give Mr. McConnelly credit. A long time ago, when I taught this, I was teaching this a very confusing way. He did it this way, so I stole his idea. This really makes it easier, so I got to give him credit for that. Okay, I'm going to put two numbers on the board and explain what this has to do with counting significant figures. Here we go. First number, 200.36. We'll say milliliters. There's a decimal point there. 200.36 versus the number 200. So this fits the conversation we just had. You know this one's more significant because it has two decimal places. This doesn't have any.
Yeah.
But the regents might make you tell it, how many significant figures in this number, how many significant figures in that number. Here's how you do it. So pay attention, wake up, do whatever you need to do, focus, because the first time I go through this is the most crucial time. Because if you learn it wrong because you're not paying attention, you're always going to be playing catch up. So pay attention. All right. Is there a decimal point? Yes.
Yeah.
So we go to the Pacific side of the number. That's why we're doing this whole Atlantic Pacific thing. Decimal point present, draw an arrow like this. We're on the left side of the number. So the number is kind of like our country. If you go to the left side, that's present, Pacific. If this is our country and there's no decimal point, it is absent, we go to the right side. Draw an arrow like that. Okay. The arrow tells me when and where I start counting my significant figures. There's only one rule. Once you figure out which side you're on, there's only one rule. You start counting with the first non-zero number, and then you keep counting until you run out of places to count. Say that again. You start counting with the first non-zero number. What's that? 1 through 9. Say no zeros. Start counting with the first non-zero number, then you keep counting until you run out of places, run out of numbers. So, let's take that and use it. I'm on the Pacific side. I start counting with the first non-zero number. Is that a non-zero number?
Yeah.
Yes. So now I keep counting until I run out of space. What does that mean? 1, 2, 3, 4, 5. I don't have any more numbers. I stop. 5 sig figs in that number right there. 1, 2, 3, 4, 5. All the numbers are significant. This one's a different story. We go to the right side. We start counting from the right.
1.
Do we start with a 0? No, you can't start counting with a 0. You skip that one. You skip that one. This only has one significant figure. One sig figure. I'm going to put 2 more numbers on the board, maybe 3, maybe 4 if the moment arises here. I'll put some numbers up, write them down, figure out the sig figs. I'll come around and check. While you're doing that, I'll hand out your homework. This is what your homework is, just counting significant figures. That's all you're doing. All right, so I'll put some numbers down, copy them, and then you're doing the same thing. Here we go. Let's go with 0.0378. Let's go with 100.05. 404. There we go. And we should have units here. Centimeters, meters, and centimeters cubed. Just for fun. So go ahead, write those down. Tell me how many sig figs each one has. And this worksheet is due tomorrow.
I assume the circles mean nothing again.
Circles mean nothing, yes.
Why do you?
Because at some point along the line, I circled them and said, don't do those, but that does not apply to you.
Also, we gotta multiply
Ew.
Well, no, it's just scientific notation. And I'm open. You're welcome. Did you tuck your shirt in today?
No.
Okay, so that's due tomorrow. Oh, I gotta check here. Hold on, let me quick do this here. Boom, boom, boom. So, put the number of sig figs next to it and circle it so I can locate it very quickly.
I'm so bad at these.
Well, we just started. Literally just started. So if you're having a hard time, that's okay.
Can it end at 0?
Yeah, you just can't start with a 0. You count all the zeros in the world, just not to start the counting.
So if it's like 0.0, we count that 0?
You can't start with a 0.
Yeah, I know, but if there's no, you can't start with any kind of 0.
You can't start with a 0
You
ever.
can't start with a 0.
Okay. So
It's like numbers 0.0.
numbers, yes, yes.
So we count that 0.0.
If there's a number before it and you're counting from that direction, yes.
Okay.
All right, we'll pick up tomorrow. But the answer was 353.
Yeah.
353.
Thank you.
Have a